Okay, hello and welcome. So today in this video we are going to discuss about tensor description of relativity. So this topic is very close to my heart because it really captures the essence of physics or the essence of relativity in our case. So what are tensors? Okay, so tensors, as I've written, they are a language to express invariance under coordinate transformation. So in the earlier videos, we have seen that there are certain quantities which are indeed invariant under the coordinate transformation. So in our case, the coordinate transformation, see, coordinate transformation is a very general word. So you can obviously apply the discussion going on here to really anywhere where the coordinate transformation is there. But right now we are interested in the relativity. So the coordinate transformation here is Lorentz transformation, where it has a particular uh, matrix to transform. It has its own matrix, which tells us how to transform the coordinates here, right? Okay. So let us see. So before even coming to this point, so we'll just circle, I mean, we'll just make a box around this uh, statement. I will explain this statement later, but to do that, we have to see how we have to build some motivation on how really vectors transform. Okay, so we have to really see that, and then we can have a look what does this statement means. Okay, let's see. So we have introduced the velocity 4 vector, if you remember u tilde from the old videos, where u tilde was gamma comma gamma by c, and then it was u vector. Okay, so that was our u tilde is the 4 vector here, and this u arrow on the head is the ordinary 3 vector of the velocity of the particle. Okay, so now let's see how we were defining this u tilde. Let us ask this question: how did we get this expression? So if you remember, we basically did something like ui. We defined ui where I was the ith component of the u4 vector, and then we defined it something like dxi by cd tau. Right? This was our definition. Now from this definition only, let's see how exactly the UI transforms. So let's say this was in one frame. This was in one frame. Let's say this was in S frame. Now what will happen in S prime frame, let's say. So in the S prime frame. So when I say S prime frame, you have to keep in mind that there is a S frame here, and then there is another S prime frame, which is moving with some velocity v. Okay. So this velocity v and this velocity u are two different. So v vector is not equal to u vector. This v velocity is of the frame S prime, and this u vector is of some particle that is going on. And u is the velocity measured in S, and u prime is measured in S prime. So u prime is the velocity of the particle in S prime frame, and u vector is the velocity vector of the particle in S frame. So I hope it is clear now which term means what. So in the S prime frame, I can define the u prime I is equal to dx prime I by c d tau. Okay. Okay, fine. Now we want to do something. Now we want to express this u prime I in terms of ui. So how do we do that? Okay, seems like a very challenging task here, but it is not. It's simple. How do we see this? So we know, because we know that dx prime I, and you have to keep in mind dx prime I is basically c dt prime, dx prime, dy prime, and dz prime. Okay. How do dx prime I exactly transform? So it transforms using Lorentz transformations, right? So we know that dx prime I is a function of x, right? So we can use the partial differentiation chain rule here. So we can simply write u prime I is equals to dx prime I divided by here we should use j because different index should be used into dxj upon cd tau. Now we know this quantity already, isn't it? It is just this one here. It is just uj, right? So we can simply write u prime I is equals to uj multiplied by dx prime I by dxj, where each of this I and j combination will be one matrix element of the Lorentz transformation matrix. So basically what it is, I will tell you. This is my, let's say, uh, gamma minus gamma beta 0 0. This was my Lorentz transformation matrix 0 0 0 0 1 0. Oops, I need one more 0 0 0 1. So here we see that you can imagine the I is the row and the j is the column. So this one's the row, this one is the column number. So it's a row number and column number. So for example, you can write dx prime 0 upon dx dou x 0. What it will be just the first element gamma, so it will be gamma, and you can check that. I mean, there is no this is no, I mean, you don't have to assume anything. You can check that. You know how dx prime transforms, and then you can simply write the expression, take the partial derivative, you will get this. Okay, it's a very simple, not very complicated thing. Dx prime 1 divided by dou x 0. I'm just telling like how you can literally see from the matrix, so that you don't have to do partial derivative each time, because you know already the matrix, so you should be able to recognize the elements from the matrix only. So what is dx prime 1 by dx 0? So prime 1 means the row number is 1, this row, and the 0th element, which is this one, right? Okay, so this is minus gamma beta. Similarly, dou x prime, let's say this time I choose row 0, but here if I do del x1, okay, so this time it will be minus gamma beta again, and then if I do 1 in both, then it would be just gamma. And now you can I mean, other elements 0 and 1, that you should be able to see for yourselves. Okay, so the ultimate thing that we got here in this notation is that something u prime I, so the 4 vector, so it is not exactly the vector, rather it is a component of the vector. So the component, 4 vector components transform by following this particular rule, x prime I j and then uj, right? Okay, so when something transforms like this, then we say that it is a tensor. So I'm giving it is a tensor component, rather, not tensor exactly, but it is a tensor component. So I'm giving the definition of a tensor. Okay. So this is the definition of a one rank tensor. So we can say that UI is a one rank tensor because there is only one index involved here. So in general, if I want to say, let's say, forget relativity, forget everything, just remember that you are in some space, and then if you do the coordinate transformation, you have a space. That means you can define some vectors, okay, and then you can define vectors as well as you can express those vectors because there is a space, so you have a coordinate system as well, right? Coordinate system. Now, how do these, when you transform, so obviously you can transform it. You can transform the coordinate system. So in this coordinate system, suppose the vectors were t, vector components were ti, and when you transform that, it becomes t prime I. Okay. So after this transformation, a tensor is something, a one rank tensor is something where this t prime I is basically del x prime I over del x I into t, sorry, del xj into tj. So this is a one rank tensor. Now what's a second rank tensor if you ask? So there is a second rank tensor where if I do something like tij, okay, where you can put index here, I mean at the top, at the superscript as well, at the subscript as well, but let's do for the superscript. So what it will do, del x prime by, but notice you have to like you have to change the indices, I mean, because it would be sometimes clutter, sometimes it's wrong also. You have to be very careful with the indices. That's all. Into del x prime j upon del x something like L and then TKL. So what is happening here? It is simply first index is being transformed here, and the second index j index is being transformed like this, and then you can represent. So this is a definition of the second rank tensor. But second rank, I mean, so there is a wording using contravariant or covariant. So like when the indices are up, so they are called contravariant. When the indices are lower, they are called covariant. So this is a two rank covariant, sorry, contravariant tensor, right? Now let's talk about, let's say, if I have Pi prime j, this is called a mixed tensor because it has one contravariant index and one covariant index. So it will be something like del x I prime I divided by del x, let's say again k, into, now because here this there is a contravariant, so it will be just inverted, right? So it would be del x L and del x prime j, and it will be summed over Tk and L. So this is a mixed tensor. I think before even giving the mixed tensor definition, I should give how we transform the covariant tensor. So it will be simply del x, uh, let's say k divided by del x prime mm, L and then Tk. Okay. So there, I think there is nothing to remember or anything. It's just that these indices, upper and lower, they are when they match upper and lower indices, so they indicate a sum, and then this one is a free index. So this is a free index, free, and these are dummy index because they are summed over. Okay. So like you can obviously you can read in more detail about tensors. So I would suggest you should read this book or lectures by Pavel Grinfeld on Introduction to Tensor Calculus. So its book name is Intro to Tensor Calculus. He has given a phenomenal level of detail of tensors, and you will really feel good and feel really motivated to learn about tensors. So yeah, should go about it. But here for our particular case, I think I'm able to justify that that using this tensor language here, it really simplifies our job. So we can simply represent how our four vector transforms it. So in our case, let's come back to relativity. So back to relativity, we have seen that what we have seen, a four vector is a tensor and it is a one rank tensor. So we can obviously write first rank of first rank. So these ideas of four vectors in relativity, they are indeed a subset of a general concept of the tensor. That is the motivation here actually. Okay, so once we have seen it, there is, now we come to this statement which I defined earlier, which is that a tensor is a language to express invariance under coordinate transformation. So right now what we have seen is, we have not seen the invariance here, we have just seen how the tensor components really transform. So all these equations in these boxes, they are saying that, okay, you have a particular tensor here, let's say our four vector here. So you have a four vector in the unprimed frame. How does that transform to the uh, in the S prime frame? So you have a four vector in S prime. How does that transform to S prime frame? So this is the equation which tells you that. But where is the invariance? I promised invariance, right? So let's now do that. Let's see. So whenever all the index of tensor are contracted. So I will define what is contraction. Are contracted, it gives an invariant quantity. And this is a mathematical statement. See, I'm not saying anything in air. This statement you can prove. This you can prove. You can prove this statement mathematically that it really happens. That when you contract a tensor, you will get an invariant quantity, and this you can prove mathematically. Okay. So let's see what a contraction means. So contraction is basically when you have a tensor, or when you have two tensor or three tensor, it doesn't matter. Basically, what it is saying is that, let's say I have a tensor here Ti, and I have a tensor, let's say Gi, okay, or J. So T is a contravariant tensor of rank 1, but G is a covariant tensor of rank 2. Now I have told you that there is something called Einstein summation notation, which tells you that repeated upper and lower index form a sum. So here you can see that the index I upper and index I up is a lower is repeated and it's summed over. Okay, so when it is summed over, it is a dummy variable, right? So the remaining will be a tensor, let's say some PG P. So it will be a tensor with only one index, lower index. So it will be, the result would be a contravariant, covariant tensor of rank 1, right? This thing also, that multiplication of two tensors give rise to a tensor. This also you can prove mathematically, but then you have to really sit back and prove each of these identities yourself. Like if I have to do that, if I want to, if I do that here, then again it will deviate us from our main topic of classical field theory. So these are all the side quests that you should do, and it really it will take time, but it will be a fruitful thing to do if you want to seriously pursue the classical field theories. Okay, so fine enough. What I was saying, yeah. So here we have seen that the contraction basically it reduces the number of indices here. Here it had two indices. This whole term had two indices, but because one index was a dummy index, so the resulting index is reduced to one. Now we can again do something very interesting. We can do, okay, we have this Pj. Now we have something, let's say Lj, and then we can sum them over, right? This is also because now J has become a dummy index, and now it will be something like sum of P0 L0 plus P1 L1 plus P2 L2, imagining that we are dealing with 4 dimensions. In general, for n-dimensional space, mathematician talk about that, so it will go on until n, but in physics, right now we are interested in 4 dimensional space, so only 4 terms. So this thing here, the PL and L when summed over, this is something which is a scalar. So it gives rise to a scalar, right? There is no index here. So when no index is there, then it becomes a scalar. So it will be something, let's call PL, okay? P and L when contracted, it gives a PL scalar. So it's a scalar with no index. Now I'm saying that PL, which is a scalar, so the scalar is something which is invariant under coordinate transformation, right? There is no index here to transform. It's a invariant under coordinate transformation, which is what I have written here. Whenever all the index of a tensor are contracted, it gives an invariant quantity, and that you can prove mathematically. Okay, so this you should try. Why it should be an invariant? I will just use this phenomenal result into the relativity. So this should be true, right? So let us not prove this in general. I will not prove it in general, but I will prove it for the case of a velocity 4 vector. Okay, I will explicitly calculate each and every term, and then I will show you why it is an invariant quantity. Okay, let's see. So we have our velocity 4 vector as something gamma comma gamma by c and u vector. So let's write explicitly what the components are. U1 is gamma, u2 is gamma by c, ux, u3 is sorry, u0 is gamma, u1 is gamma by cx, u2 is gamma by c uy, and u3 is gamma by c uz. Okay, fine enough. So now what we can do is we have to do something like, let's see what the term ui and ui means. So here what we are doing is we are simply contracting the u's here, the u contravariant and covariant. Okay, that is something. And now one thing is there that you know the u contravariant component. So you know here the contravariant components gamma, gamma by c ux, gamma by c uy, gamma by c uz, but you do not know. So here we don't know the covariant component ui's. Oh no, big trouble, big trouble. Okay, no worries, no worries. Let us try to figure out what UI should be. Okay, since we do not know the UI, we cannot really put that here and see the contraction, calculate the contraction. But what we can do, we there is still a hope. There is a hope. The hope is that when we had dxi as something c dt, dx, dy, dz. Okay, and we know that dx ds square, when we find ds square, it was c dt square minus dx square minus dy square minus dz square. This was an invariant quantity, so this was invariant, so this we know. Now we want to fit in the invariance of ds square into this notation to find out what dxi exactly should be. So we should be able to calculate the figure out what dxi or rather covariant dxi's are, given that our contravariant dxi are this, and given that this quantity is invariant. Okay, so what if we do something like dxi and dxi, upper and lower? Now from the mathematical theorem of tensor, that when you construct two tensors, it should be invariant quantity. So this should be equal to my c dt square minus dx square minus dy square minus dz square. Am I right? Okay. So we know that dxi is that. Now what should be dxi? Small, with the in the subscript. So it is not very hard to see that dxi should be something c dt and the sign reverse for the spatial component, something like this. So here what we have got the contravariant components like this and the covariant components like this. Because we are implying this particular notation so that the contraction gives you an invariant quantity, and we know that this is invariant. So taking inspiration from this result, we can simply say that okay, then probably our u subscript i's or contravariant 4 vector velocity 4 vectors should be something like, you keep the time component same, first component same, and then you do the minus sign on the spatial components. Okay, that is easy. So we have done this, right? Okay. Now what we can do? Now we can calculate the contraction. So here the contraction would be again u0 plus u1 plus u2 plus u3 correct. But then we can see that u0 and u0 is it's same, it is gamma square, but because of this sign reversal here, it would be simply gamma square by c square into u vector square. Should be able to see that. It's very easy. Something here we are getting the space time component square. Oh sorry, it should be c square. So space component square, and with the time time component square is with plus sign, and all other are with negative sign. So let's see what, so it should be invariant, right? So we are claiming that this quantity should be invariant, and that is what we are implying. That should be written from the R tensor notation. Okay, let's see if it is the case or not. So it is gamma square 1 minus u square by c square. But what is 1 minus u square by c square? So 1 minus u square by c square nothing but 1 upon gamma. So it should be gamma square by gamma square, which is 1. So ui contracted, it is 1, and you know that 1 will be 1 in S frame and S prime frame same. Okay, so it is an invariant quantity. It is a scalar. So we have indeed proved that the four velocity vector is is a tensor, and then when contracted, when covariant and contravariant is contracted, covariant, contravariant. So this is, sorry, this is contravariant, and very, I really confused between co and contra. Covariant and contravariant when contracted, it gives a scalar. So yeah, that is what I started with here, that whenever all the index of a tensor are contracted, it gives an invariant quantity, and that we have proven that for r velocity 4 vector. Now this is in general true for all of the vectors and tensors around here, because vectors are also tensors, scalars are also tensors. So tensor is a more general class, right? So that's what it is. Okay, so I think there are two aspects we should remember, that a contravariant tensor transforms like this. This you should make peace with, and the covariant tensor. So once you know, once you get this u prime I here, so we got this u prime I from our motivation from here, right? From our motivation of dxi. So from the dxi, we got the motivation to define ui, covariant ui. But then now here you can, once you got the ui, you can prove this thing also. So nothing has to be, nothing has to be really assumed. So you can prove everything in here. So it's not a problem. So dxj, dx prime I, and you, uh, no, it's always a little bit problematic for me. J. Okay. Yeah. So this you should be able to prove now. So this you can prove it now using the definition of UI given above. And this definition we have motivated it from the in space-time interval invariant. So everything in relativity is, majority of the things are originating from the space-time interval invariant, and that's why it is so important concept in relativity. And we are building structure over it. So that's what. Now, after proving this, the final thing that I would like to do is that when you we have here, so basically what we had, again I will write ui, let's say u0 and u1 and u2 and u3, okay, but u covariant I was u0 and minus u1 and minus u2 and minus u3. So indeed there is a very nice way to represent this particular property also, that covariant tensors, covariant components are just negative times the space components of the contravariant tensor. So you can represent this ui using something like eta ij and uj. Bear with me, I'm introducing new and new symbols, but it will be worthy. They are very general things. So, what is a eta ij? Okay, so eta ij you can imagine. So, what is exactly happening here? I will tell you. So, first of all, ui is basically eta I0 u0. It is a sum, right? Einstein summation 1 to 1 I2 u2 plus eta I3 u3. Now, you can obviously for so you can obviously write this particular thing in a matrix form, right? Because then I forms a matrix. I also has goes from 0 to 3. So obviously you can write something like u0, u1, u2, u3 as a matrix here. and then u1, u2, sorry, u0, u1, u2, and u3. Now, what is the matrix here exactly? So we see that the matrix should be such that it does not change the time component, but it changes the space components. Okay, and the second thing to realize is that there is no mixing of the component. So what I mean by that is that there are only like what here it means is that u0, let's say, so u0 is equal to u0 and u1 is equal to minus u1, right? So there is no sum over u2, u3 and u4. I mean u2 and u3. u1, 1 here, right? Similarly, u2 is equal to minus u of contravariant 2. So 2 here, 2 here, no additional sum. So that motivates us to say that this matrix is a diagonal matrix with diagonal elements, sorry, diagonal elements arranged like this. 0, 0, 0, 0, 0. Everything should be 0 here. Should be a diagonal matrix. So this particular quantity, now in some books what you can see is that some books this is being negative and the others are positive. That is totally fine. It just, I mean, if you pull out, keep the minus sign here and there will be no problem, but you have to stick with one particular definition of space-time interval. So you have to, so this is what is called a signature of a metric. So either the signature will be 1, minus 1, minus 1, minus 1, or it will be a minus 1, 1, 1, 1. So in Landau-Lifshitz, we are following this signature. So we will stick with this signature of metric. So this matrix or rather eta ij is called a metric tensor. This thing is called a metric tensor. Now another exercise what you can do is you can prove that it is a tensor. First of all, you have to prove that it is a tensor. I am just saying that it is a tensor, but you can prove that it is a tensor. How you will prove? You will prove using these definitions of tensor here. How tensor transforms. Every time if you have to prove anything, how tensor transforms, you have to look at these definitions. Even though I only have this ij up, but when you have ij down, you will be able to transform something like this. Just read some book or lectures, rather not any random book or lecture. I would really prefer. I would rather suggest you to read this book's Pavel Grinfeld lectures so that you will be able to grasp all the concepts. So this thing here, when I'm defining, this is called index lowering, which Pavel Grinfeld also called index juggling in his book and lectures. So yes, so my final thing was here that we can write the covariant components. So basically the idea here is that the metric tensor lowers the contravariant components of vector here. So finally, as an end result, we can write what we can do is we can write this ui and ui in terms of metric. So just keep the u upper I same, but just now we have seen that u lower I can be written as eta ij uj. So we can simply write this as eta ij ui uj. And here also you can see that so I is contracted, j is contracted, so it should be a scalar. And when it is a scalar, it is also should be invariant. And we have seen in our case here that it is equal to 1. Similarly, you can write the invariance of space-time interval also. We write dxi where we have defined what dxi is exactly. Again, we can write it in terms of eta ij dxi dxj. So this is also an invariant quantity. This is also invariant because it is contracted. So I think even though it might be all confusing, but if you go from that book of Pavel Grinfeld, solving some topics, I mean, in Euclidean geometry, if you just solve some problems and prove some theorems, you will be home, and you will really appreciate the quantities here, these metric tensor and the invariance. So I think we have built enough foundation for the special relativity and its treatment in terms of tensor algebra. So next time what we can do is we'll be looking at forming the Lagrangian uh, for the relativistic mechanics, and then we'll move on to the relativistic dynamics, and then obviously to the how in relativistic dynamics, how particles interact with each other via fields. So that is what the classical field theory is. But yeah, until this point, it should be very, very clear to you what these quantities means, what is the physical significance. I really want to explain each and everything, but I am limited by time, and because if I do that, they're all courses in themselves. There will be a lecture series in themselves. People have made them. I am suggesting you to watch it and then you come back to continue from here.